Okay, well, let's get started. I'm pretty happy today because of what happened yesterday. And what happened yesterday was this lunar eclipse that I hope many of you saw. I'll just say a word about homework. This, by the way, is lecture 12 of the planets, if I'm doing the counting right. And the homework is just to do Chapter 9. Chapter 9 is sort of, in some ways, the heart of the semester. It's about rocky planets that we've been talking about the last two lectures. And so by reading Chapter 9, you'll learn about the four rocky planets in our solar system, Mercury, Venus, Earth, and Mars, that we've been discussing. The interiors, the surface crusts, the plate tectonics, the volcanoes, and the origin and fate of rocky planets, and how our planet Earth fits into the grand scheme of rocky planets in general. So by all means, find time, if you haven't already, to read Chapter 9 and do the homework in Mastering Astronomy. It, of course, is due, as always, tomorrow, Friday, at 6 p.m. If you want to peek forward, next week is on Chapter 10, on the atmospheres of rocky planets. And that's one of my favorite chapters in the whole semester. So by all means, if you want, have some fun and look forward, read Chapter 10. But first things first with Chapter 9. We were lucky. Those of you who got up at 3:30 a.m. in the morning were treated to something that happens only once every few years, and that is a lunar eclipse, a full, total lunar eclipse. And so it was really quite a treat. Let me ask for a show of hands. How many of you got to see the lunar eclipse? Almost everybody. That's really great. There is an observing project to turn in. It's very easy. All that I ask you to do is make a sketch, take no more than 2 or 3 minutes, sketch what the moon looked like to you during totality, and turn it in either today after class if you have it, or on Tuesday before lecture or after lecture. And I don't want any words. This was supposed to be fun. You'll get full credit if you drew a sketch that looked anything like the moon during eclipse. And I'm even going to show you what the answer is in a second. So this was really a lucky opportunity. In all my years of teaching, I've never had a class that had an eclipse that occurred during the semester. That's how rare they are. So you got to see something pretty special. I actually came to campus. I don't know how many of you woke up and are living near the periphery of campus, but I came into campus and I wanted to view the eclipse right from campus, and I wanted to show you a couple of pictures I took with my little camera. This is maybe, could we have the room lights down in the back there? We could see it a little bit better. Yeah. So this was standing on campus, the Campanile, of course, and there's the moon, sort of dark. One little corner of it was brighter because the umbra, the shadow of the Earth that falls on the moon during an eclipse, the shadow wasn't perfectly centered. So one edge of the moon was a little bit brighter even during eclipse. Here's another picture I took. Campanile, and there's the moon. And I think I took one more. Yeah, here's one. So even with your camera, you could take a picture of the moon during its eclipse, and it's rather impressive to see that red, sort of brownish red color to the moon. It's not just dark, it's kind of a dark red. And the reason has to do with something you already know about. The Earth's sky, our Earth's atmosphere, scatters blue light more efficiently than it scatters the red light. So when the sunlight comes in, light comes in from the sun, hits the molecules in the Earth's atmosphere, And the bluer photons scatter from the Earth's atmosphere more efficiently than the yellow and red photons. And so the sky is blue. Our Earth's atmosphere, you look up on a nice clear day, the sky is blue, and that's because the blue photons are getting scattered more. The moon, however, looks red because sunlight during an eclipse is skimming through the Earth's atmosphere and being refracted, bent by the Earth's atmosphere. The blue photons get scattered away. Even the green ones at short wavelengths, both of them short wavelengths, get scattered away, leaving the surviving photons, which are the yellow, the orange, and the red photons that make it through when they skim through the Earth's atmosphere, get bent and bend around the Earth, making it to the moon. So the moon gets illuminated by sunlight that was bent as it passed through the Earth's atmosphere, the blue light mostly being scattered away, leaving predominantly the orange and the red light. So that's why the moon looks so red. Pretty exciting. You can bring the room lights up again if you'd like. So I'm so happy that many of you got to see this lunar eclipse. It's quite a rarity, the last one occurring 3 years ago, and so it was quite a treat. I want to just review one thing we talked about last time. We humans have an exquisitely good knowledge of the interior of our own planet Earth by using sound waves, seismic waves launched by earthquakes. And I'll remind you what we talked about last time, that there are two types of these seismic waves, the shear or S waves and the P waves. And you may remember that we did a human demonstration. The shear waves represent displacements perpendicular to the direction of the motion of the wave, and the P waves involve displacements of the material parallel to the direction of the motion. And you may remember that we constructed out of our own human bodies a human seismic wave, both a P and an S wave, and there we are during class 2 days ago. And if you're interested, I have a video of our own seismic wave. Would you like to see the video of us? It's kind of a seismic selfie. Hang on a second. I think you'd probably like to hear the sound of this, although maybe not. I don't know. Okay, you ready? I'm going to push this poor guy right here. Longitudinally, I'm going to push him sideways because I'm hoping the wave will propagate in the direction that I push as a compression wave. And you should all just sort of stand there limp and let the pressure, take you over. All right? Are you ready? Your shoulders need to be touching somebody next to you, or very nearly. Some people are lacking slackers. All right, you ready? Here we go. I'm going to push. Yay! So that's a P wave because you were moving as an individual human being like a molecule of rock. You were moving in the direction that the propagation of the P seismic wave was itself going. Now we're going to try the harder one. And this one, it's a little touchy-feely. You have to link arms with the person next to you. So link arms with the person next to you, except I'm not going to do your arms. You're going to be the last one. So here's what I'm going to do. I'm going to move perpendicular to the direction of propagation. I'm going to move downward, yank this poor guy downward, and if you're all linked arm in arm, you'll see what happens. Are you ready? Here we go. I think we did a good job there. It's pretty exciting to think that by analyzing seismic waves, S waves and P waves, that travel through the Earth, bounce off the surface, and are received by seismometers, geophysicists can analyze the travel time, the location of those waves, to determine what the structure of the Earth is, the mineralogy, the density, the temperature, and the type of minerals in the Earth as you move outward from the core all the way to the surface. And you remember that there were three main components of the Earth and other rocky planets: the core, the mantle, and the crust. And the core of the Earth has two parts: the inner solid part and then the outer core, which is liquid. And we know that because the shear waves do not travel through liquid, so they get shielded, they get absorbed. The S waves do as they hit the outer core. Okay. Turn over a new page in your notes, at least mentally. Today we're going to spend the entire lecture on the planet Mars. And the planet Mars is special. Of all the planets in our solar system, it's the one planet that, frankly, we humans have a chance of visiting and perhaps someday colonizing. And maybe within your lifetimes, there will be humans traveling to Mars, setting up shop, setting up homes, maybe even having families. So Mars is an interesting place. It does present promise because of the rocky surface you can walk on, the light atmosphere that could be added to, the presence of water that we'll talk about. Mars, of course, also presents some challenges. There's not any oxygen in the atmosphere. There isn't any liquid water on the surface. And the temperature is about minus 60 degrees Celsius. So it's not exactly a tropical rainforest on Mars. And some sort of how shall I say, biological engineering would be required to make Mars suitable for life. But I'd like to talk about everything we know about Mars with an eye toward the day when you or your children or your grandchildren might be the first inhabitants of Mars. Now, first of all, what do we know from telescope observations? Well, quite a bit. There's a picture of Mars taken from the Hubble Space Telescope. You immediately see many of the main features of Mars. It has a polar cap. It's composed of water, mostly. Some solid carbon dioxide as well. But there are polar caps, like the Earth has today. And by the way, I can imagine in 100 years, when your grandchildren are the first people to travel and maybe colonize Mars, Mars will have polar caps, but the Earth perhaps won't. So it's interesting that Mars may be the last vestige of polar caps in the solar system. The surface of Mars is a orangey reddish color. You can see that by just looking at it with your naked eye, that all of you have done. When you saw Mars in the night sky, remember, it looked a little yellowy, maybe orangey. And you can see that clearly in this picture. That's because the surface of Mars is rusted. It is iron oxides, like you see in the southwest deserts of the United States, in Arizona, New Mexico, southern Utah. That iron oxide rock that's been rusted takes on a reddish color. So you can almost taste the rusted rocks, just by looking at Mars. Clearly it has polar caps. You can also see evidence of storms. You see sort of what look like clouds here, 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 here. They come and go every hour. So there are some kind of winds that kick up the dust, and the dust storms come and go more or less like they do on the Earth. So there's clearly an atmosphere, and it's windy, and you can see that in the dust storms just by taking a picture. You can spread the light out from Mars into all of its wavelengths, blue, green, yellow, red, including the infrared and the ultraviolet, as you all know, and analyze that spectrum of wavelengths for the chemical composition of Mars. And when you do that, you find out that the atmosphere is almost pure carbon dioxide. Nothing like the Earth's atmosphere that we'll talk about next week. Earth's atmosphere is mostly nitrogen with some oxygen, obviously, that you breathe. But on Mars, it's all carbon dioxide. The polar caps, as I said, are water plus carbon dioxide. As I'll mention in a few minutes, the atmosphere of Mars, however, is very thin, 1/100th the density of air that we breathe here on the Earth. So Mars's atmosphere is about 1% of the richness of our own Earth's atmosphere. Let me now go through a list. It's a little bit mechanical, but I'd like to go through a list that compares the properties of Mars to the properties of the Earth, one by one. And the first thing I can show you, of course, is that Mars is smaller than the Earth. It's about half the size and about a tenth the mass. So something worth remembering, I normally wouldn't ask you to remember anything, but it's a nice take-home memory from this course. Mars is half the size of the Earth and about a tenth of the mass of the Earth. Of course, Mars is farther from the sun than the Earth is, so Mars is cooler. It receives less sunlight per square meter than does a patch of square meter on the Earth. So that reduced sunlight means Mars is cooler. Mars has an axis tilt that's about the same as the axis tilt of the Earth, something like 23 degrees or so. But that tilt of Mars's spin axis changes. It flops around. It's not steady like the Earth's spin axis. And the reason is twofold. First, Mars does not have a big moon, as we do. So Mars has a spin that's not stabilized by a big moon like our own moon stabilizes the spin of the Earth. And the other aspect of Mars's spin that causes it to flop around is that Jupiter is closer to Mars. And Jupiter pulls gravitationally on Mars, causing the spin axis to wobble around a fair amount. Mars has a spin period, i.e. a day, a Martian day, is about the same length of time as our day. It's, I think, a little more than 24 hours. Mars also is in an orbit that's more elliptical than the Earth's orbit, which is nearly circular. So Mars, you may remember, it was Tycho Brahe that noticed the retrograde motion of Mars, the strange behavior of Mars as it goes around the night sky, and Kepler took that into account, noting that Mars's orbit was clearly not circular, but instead elongated, elliptical. So those are the aspects of Mars that you can keep in mind. Few more aspects of Mars. versus the Earth, 1 year is 686 days. So Mars has an orbital period that's about 2 years, not 1 year. And of course that follows from Kepler's third law. Mars is farther from the sun than the Earth is. So that larger orbital distance, p squared equals a cubed, means that Mars takes longer to go around the sun. Because it's smaller, the gravity is less on Mars, only about 38% of the gravity on the Earth. So you could jump 3 times farther on Mars than you can on the Earth. And as I mentioned, Mars being farther away, it receives less sunlight, about 44%. And then most importantly is the atmosphere. You see, the atmosphere of the Earth, as we all know, is nitrogen and oxygen. But for Mars, it's almost all CO2, carbon dioxide, trace amounts of other molecules in Mars's atmosphere. Mars has lots of properties in common with the Earth, but lots of differences. One thing I want to mention again is the elliptical orbit of Mars. If you look here on the right, it gives you a better view. There's the sun, there's the Earth in its nearly circular orbit, and here's Mars in its more elongated elliptical orbit. You see over here Mars was close to the sun, and then over here Mars is farther from the sun. We all know that the seasons on the planet Earth arise due to the tilt of the Earth's spin axis, not due to the closeness or distance of Earth from the sun. But on Mars it's a little different because Mars really does change its distance from the sun. And it just so happens that in the northern hemisphere there are brief, mild winters, and it also has, the northern hemisphere does, long, cool summers. Why? Well, because on Mars, when the spin axis of Mars is tilted toward the sun, i.e. it should be summer, it's true, but Mars happens to be farthest from the sun when its tilt axis, spin axis, is pointing toward the sun. I think I said that right. So when the spin axis of Mars is pointed toward the sun, Mars is farther from the sun. And remember, when a planet is far from the sun, it moves more slowly. And so Mars spends a longer time during summer in the northern hemisphere because even though the tilt axis is pointed toward the sun, Mars is at its farthest distance from the sun, and that causes the summer to be more mild and to last longer. And then the reverse is true for the winter in the northern hemisphere, and you could go through the same argument for the southern hemisphere. Southern hemisphere has long, cold winters and a brief but hot summer. And again, the seasons still occur on Mars because of the tilt of the spin axis, but the seasons are modified slightly because Mars is sometimes farther from or closer to the sun. So that's a little different. And here's another depiction. There's the tilt of the spin axis of Mars, similar to the Earth's right now, but actually Mars, as I mentioned, has its spin axis wobble around as Jupiter yanks on Mars, and Mars does not enjoy the presence of a large moon like we do that stabilizes the spin. We've learned a lot about Mars, not just from taking pictures, but even more specifically from sending spacecraft to Mars. And in the last 40 years, we humans, especially the United States, has spent quite a number of spacecraft to the surface of Mars and also orbiting just around Mars. I think right now we have 4 or 5 spacecraft at Mars right now, functioning, taking data. We have several orbiting spacecraft around Mars, taking pictures every minute of your life, and we have several rovers on the surface of Mars. And here's sort of a a quick summary, you're never going to remember all this, but there was the Viking spacecraft in 1976, Pathfinder in 99. It was a little skateboard, no joke. Mars Global Surveyor, Mars Odyssey, Mars Express, Mars Exploration rovers that were sent there 7 or 8 years ago. The rovers were very exciting. Let me show you a picture of the 2 rovers. They had names, Spirit and Opportunity. They look like this. You can see they were a little bigger than a skateboard, but not much bigger, with cameras, spectrometers, various types of mineral analyzing equipment that I'll mention in a few moments. But these 2 identical rovers spent several years moving 100 meters per day, a football field length per day, analyzing the rocks, taking pictures, studying the chemical composition, the water content of Mars. One of them was in this place called Meridiani Planum, and I have one picture here. I just love this picture of Mars, right down here. You see some bare rock that's been exposed. A lucky thing, because on Mars there's so violent dust storms that Mars is covered with dust. But here the dust was blown away and you could see the bare rock. And it looks very much like, again, the southwest portion of the United States. If you go hiking in the hills in Southern California or in Arizona or Nevada or New Mexico, it looks a lot like this. And this is very characteristic of sedimentary rock, where layers of sand and dirt have been brought in by water and layered. And so here you're seeing evidence of the same geology on Mars that we have on the Earth. And then a few years ago, I guess 2008, I was pretty excited by this. There was a lander called Phoenix. What was exciting about it was that Phoenix landed near the North Pole of Mars. That's brilliant, right? If you're interested in knowing whether there's water on Mars and whether there might be somewhere some liquid water on Mars, or maybe liquid water under the surface of Mars, why not send your lander right to a place where you already know that there's water, namely the polar caps? So there's Phoenix landing. They are the engineers at the Jet Propulsion Laboratory, electronics and optical and mechanical engineers, system engineers building it. And then it landed near patches of ice. And indeed, it took pictures of patches of ice while Phoenix was operational. You can see where it landed near the outskirts of the polar cap of Mars. And it took many, many pictures of the ice sitting on the surface. I'll show you some a little later in today's lecture. And what I loved about those pictures of the ice on Mars, it sort of reminds you of, a winter vacation here on the Earth. But moreover, as the weeks went by, the sunlight would hit the ice and it would vaporize. The ice would go away, just as it does on a warm day here on the Earth. So that was, I think, very exciting, but also a little bit sad. And it's sad because of something I'll mention in a few minutes, but I'll mention it right now. On Mars, the atmospheric pressure is so low that water, when frozen, looks just like normal ice. But as it warms up, it transforms directly into vapor. Sublimates is the word that's used. There is no liquid phase of water on Mars. Water cannot be liquid on Mars because the pressure is too low. I'll come back to this in a moment, but it's very worrisome that water in liquid form cannot exist on the surface of Mars because the pressure is too low. As you warm up ice, it goes directly into steam, gaseous, vapor, water. Now, most excitingly, a year and a half ago, I guess now 2 years ago, the most elaborate, sophisticated geology laboratory was sent to Mars in a spacecraft called Curiosity. It's still there. It's roaming over the surface of Mars right now. And I'm going to spend the next 10 minutes telling you what Curiosity is doing on Mars right now, day after day, as you live your life. Curiosity is sort of a geology lab working by itself robotically. It landed 2 years ago, but the landing itself was dramatic. This laboratory, which I'll describe in detail in a minute, is the size of an automobile. How do you send an automobile to Mars and preserve the cameras and the spectrometers and the X-ray spectrometers, the other sophisticated sensitive equipment that I'll describe? How do you send a piece of scientific equipment the size of an automobile to Mars and land that automobile safely without destroying or damaging any of that equipment? Well, the engineers at the Jet Propulsion Laboratory in Pasadena worked very hard, and for a long time they had no solution at all as to how to transport and land a lab the size of an automobile on Mars. And I want to show you a video that describes how the engineers figured out a way to land this Curiosity lab on Mars. Okay, that was scary. But it actually worked. And what I love about this video of the challenge of landing, a giant piece of scientific equipment on Mars is it's hard. I mean, this is many years of work. People devoted their careers to just figuring out every engineering detail of that landing approach. So it's an exciting prospect. Any of you that are interested in engineering or chemistry or controls or computer programming, you can work for NASA or for the companies that take contracts from NASA, and you can be a part of the teams that build these spacecraft, land on Mars, go to the other planets, and so on. It's a whole exciting area of creative, challenging work in and of itself. So, Curiosity has landed a couple of years ago on Mars. Everything works. And they purposely landed the spacecraft on a crater, inside a crater. And you can see in August of 2012, it landed at this latitude and longitude by this so-called Gale crater. And the crater, of course, like all other craters, was formed when a meteor hit Mars and blasted this crater in Mars. You can even see the central rebound there. And the reason that the scientists chose Gale crater was that there was prior evidence from previous missions for water in ice form being there at the Gale crater. Now, the Curiosity device actually is composed of many experiments. And to be honest with you, most of these are more complicated than we want to deal with today, but I wanted to give you a sense, a feeling for the level of sophistication of the diagnostic instruments that are a part of Curiosity. And so I'll just walk you through these. They're listed down here to the lower right. There is, first and foremost, a camera. And it's called Mast Cam right here. It's a camera that I'll describe in a couple of minutes how it takes color pictures of Mars. It turns out it's not that easy. There's a alpha X-ray spectrometer, which I'll describe in a few minutes, to analyze the minerals. There's something called ChemMin, which is another device that takes spectra of flame-broiled minerals to determine the chemical composition of those minerals. And you see there are various other devices around here. Let me start with the camera, because we all want to see the pictures that Curiosity took. This is the camera. It has lenses in here, a baffling, and then a digital so-called CCD detector back at the bottom here that actually takes the pictures. It can take video, 10 frames per second. And most excitingly, it can take color pictures. But it doesn't do this the way a normal camera works here on the Earth. A normal color camera on the Earth has pixels that are individually sensitive to red, green, and blue. Instead, the mast cam works as shown below on Mars. It has a CCD light detector that is sensitive to all of the colors simultaneously, and the way it takes color pictures is with a filter wheel. So this filter wheel has filters in it that pass the red light, orange, blue, green, white, and so on. And this thing spins around, and when light from a particular color, like say the blue light, passes through the blue filter, then this camera takes a snapshot, and then a moment later takes a snapshot through the green and the orange and the red as it spins. And then in digital signal processing, you can paste together, add together the pictures taken through each of the filters and end up with a color picture. Now, this isn't as easy as it sounds, because you never know exactly how much of the red to add to how much of the green to add to how much of the blue. And so the engineers work pretty hard at getting color balance. They take pictures of white sheets of paper to try to get the color balance right, and they have to do this at Mars. So you can see here are 3 scenes that are identical. They're the same 3 pictures, but with different color rendering. So there's a whole field of image processing by which the colors taken by a spacecraft are tuned and balanced to get a true rendering. And I think the one on the right is the best rendering of Mars. You can still see some of the orangey brown surface from the iron oxide, but it's not a silly sort of overdone color rendering. This is more realistic. Then there's a really exciting instrument on Curiosity called the alpha particle X-ray spectrometer. This thing shoots alpha particles. What's an alpha particle? Well, it's just helium. The nucleus of a helium atom that you see here to the left. A helium nucleus in particle physics is called an alpha particle. Shoots alpha particles at the minerals and receives the X-rays that come off of the atoms of which the minerals are composed. So these alpha particles interact with the atoms, knock electrons out of their orbits. Remember how atoms have electrons in their bound orbits, quantum orbits. And then when the atom responds by having electrons fill back in to those energy levels, they spit off X-rays. And so this device bashes the minerals with alpha particles and collects the X-rays to determine what type of elements. After all, when you look at a rock, how do you know what atoms are inside that rock? This thing shoots alpha particles at the rock, excites the atoms, they de-excite, spitting off X-rays that have characteristic energies, and they can be analyzed to determine which atoms were in there. So it's a great way to learn what Mars is made of. And then there's something called ChemCam. This is my favorite. This crazy device, as you can see, has a laser. It shoots the minerals with the laser and vaporizes some of them. It breaks the rock up, vaporizes it, and these vaporized material can then, now in atomic form, will emit light because they've been heated up. the electrons, now excited, drop back down to lower energy levels. And so by heating the minerals with this laser, you can then, again, learn what the chemical composition, the atomic composition of the rock might be. And I have to say, one of the most important efforts by the Curiosity mission was an attempt to detect methane gas. Now let me remind you, methane gas, methane is just carbon at one carbon atom and 4 hydrogen atoms, CH4. That's methane. And methane as a molecule comes from the decay of plants and animals. And so here on the Earth, where you see methane, that methane came from bacteria, plant life, etc. And so this device was attempting to look for methane gas on Mars as a sign that there was some bacterial life, perhaps, buried in the rocks, maybe under the surface, maybe where there's some liquid water, giving off methane that we would then be able to sense and realize that there must be life on Mars, maybe microbial bacterial life under the surface, giving off methane. And what was disappointing was that they didn't find any. No methane was found at all. And you can see it talks about the disappointment. The Curiosity rover has scanned Mars for methane every day, but has not found any, which probably means it does not support life. And it goes on to talk about it could have been that microbes might have produced methane gas beneath the surface, but they didn't find any. So we are still looking for life elsewhere in the universe, not just on Mars, but everywhere else. Mars is a good chance, a good place to hunt. There's certainly water there, maybe liquid water under the surface, but so far, still to this day, no sign of life on Mars. There's another X-ray diffraction experiment. I'm only going to mention it briefly. This instrument shoots X-rays at the minerals and looks to see the X-rays that diffract interferometrically out of the minerals. Don't worry about what those words mean. They're not important. But this is one common way that geologists on the Earth analyze rocks for their composition, and so it is with this X-ray diffraction device on Mars. One of the things that I love doing is just looking at pictures of Mars and trying to get a feeling for the history, the nature. What would it be like to live on Mars? And so here are a few pictures of Mars. You can see it looks very much like a desert southwest United States landscape, except there are some major differences. One of those differences is Mars has a temperature of minus 63 degrees Celsius. You better bring your parka the next time you go to Mars. It is frigid beyond the Arctic here on the Earth. Sometimes it gets down to minus 110 degrees Celsius. Remember, 0 degrees Celsius is freezing, what we would call 32 Fahrenheit. So it is cold on Mars because it's far from the sun. Any colony on Mars where we humans might live is going to need a pretty serious space heater. There are obviously geological processes on Mars, and obviously the rocks and the landscape look a lot like the Earth, so there must be geological processes, volcanism, or maybe in the past plate tectonics, some kind of melting from impacts or volcanoes and solidification that causes the basalt-like rocks, these dark basalt rocks that you see. So between volcanoes and impacts, there's a lot of similarity in the geology of Mars to that of the Earth. And there are even some dry river channels that I'll show in a couple of minutes. And one thing I want to remind you of is the number of craters on Mars compared to the Earth is simply due to the fact that here on the Earth, the craters happened but they got smoothed over by erosion. Wind, water, snow, volcanism paves over the Earth. And so the craters that were obviously here in the same numbers and density as the craters on Mars, they have vanished for the most part here on the Earth. But they certainly happened. By the way, the Earth must have suffered way more impacts from asteroids and comets than did Mars. Why did the Earth suffer more impacts? Because the Earth is 10 times more massive, and therefore the Earth gravitationally attracted the comets and the asteroids. So early in the Earth's history, the first 100 million years, there must have been titanic collisions occurring almost daily as the Earth gravitationally brought in, focused in, attracted in the asteroids and the comets, making many, many craters. Mars shows this enormous number of impacts, but the Earth, it must have been even more horrific. It's just that erosion has covered them up. But I do love looking at the pictures of Mars. You could imagine your hiking boots on and some water and a little bit of food, and you could take some nice hikes on the surface of Mars. Wouldn't that be something? And there are mountains, you see. You could imagine hiking and trying to climb a mountain one day. There's some tall ones. Be great to take a hike on Mars. But you better bring some water, liquid water, because Mars doesn't have any. It has water, I'm making the distinction, in the form of ice that we've talked about. And there may well have been liquid water in the past. Liquid water in the past. But liquid water, as I've mentioned, cannot persist on Mars today because the pressure is too low and the temperature is too low. Any water would be freezing, and to whatever extent it might warm up somewhere on Mars, immediately the ice would sublimate into water vapor, not liquid running water. And the reason for this is something well known to the physicists and the chemists. Don't bother with this graph, but it's just to show that in the laboratory, you can measure the properties of water as a function of its pressure and its temperature. And depending on the temperature and the pressure, water is either ice, vapor, or liquid, which is the prerequisite for biology. And you can see that when the pressure is low and the temperature is low, you're way down over here in this region, you only have ice directly to vapor. Low pressure, low temperature, ice, and vapor. There is no liquid phase of water possible on Mars, just thermodynamically impossible. So even if you could warm up Mars, it wouldn't help. What we do need to do is increase the atmospheric pressure on Mars. If the pressure were higher, then the ice, when warmed up, would become liquid. Maybe someday, 100 or 200 years from now, we will pump up the atmosphere of Mars and make the atmosphere have higher pressure and therefore allow liquid lakes, oceans, rivers, and so on Mars, rendering Mars suitable for human existence. Of course, there are polar caps on Mars, as I've mentioned several times, showing that there's water. But moreover, there are craters that shadow the sun so you can see big patches of ice. And you can even see ice around the perimeter of the crater. So there's plenty of water on Mars, but it's all bottled up in the form of ice or vapor in the atmosphere. But I think it's pretty cool to see how much water there is. You could imagine 50 years from now, we humans send people to Mars, build a colony, and bring in the ice to melt it so that we can use it as the liquid water that we need to live. There are spacecraft orbiting Mars that can measure the amount of water trapped in the minerals, trapped in the soil of Mars. And this is one such experiment. The Mars Odyssey gamma ray spectrometer was able to measure how much water was trapped in the form of ice in the dirt on the surface. And red represents low amounts of water. Blue represents high amount of water, if you see the scale up here. And so you can see near the polar caps, there's lots of water trapped in the rocks, trapped in the dirt on the surface of Mars, and even near the equatorial regions, there's some water. So there's plenty of water on Mars. There's also water in the atmosphere of Mars, easily measured by spectroscopy. So the atmosphere and the polar caps have water, and as shown here, even the dirt, the minerals on the surface have water. Now I want to talk a little bit about the prospects of liquid water on Mars. And there's evidence, and it's bizarre, that there was in the past, momentarily, maybe for longer periods of time, liquid water on Mars. And the best evidence comes from looking at the slopes of craters or the slopes of mountains on Mars. You can easily see the dry riverbeds just like you do on the Earth. Certainly there were moments of liquid water somehow that spurted out, flowed down these slopes, and carved by erosion these dry riverbeds. They're called gullies, Martian gullies. You see it here, here, lots of them here. These are pictures of Mars clearly showing that at least momentarily there was liquid water. Here's some more. You see the gullies. They look just like canyons that would flood when it rains here on the Earth. So there's the crater. There's a blow-up of this little edge of the crater. It appears, because dust storms would cover up these gullies, it appears that this liquid water existed recently, in the last million years or so, maybe even more recently, maybe even every day. But obviously, because of what I said thermodynamically, liquid water can't be there for any long period of time. But maybe for an hour or for some number of minutes, a geyser occurs. Water pours out from the interior, spills down the slope, and carves out a canyon from that river momentarily. These gullies are quite beautiful and quite dramatic. You see them all over the sides of craters. Look at that beautiful thing. So there are rivers momentarily. In addition, when you look at the geology of Mars, and I'm no expert on geology, but this is pretty obvious. If you've ever gone to the Grand Canyon, you probably had somebody explain to you why on the Earth there is this layered pattern of rock in the Grand Canyon. And the reason, I think many of you know, is that early in the history of the region of the Grand Canyon, over the last few millions of years, there was liquid water, of course. The liquid water flowed over the surface, maybe even in the form of lakes or oceans. And the layering you see here is the result of the deposits of the silt, the dirt that was suspended in the water, dropped down and produced year after year after year the layers that you see in the Grand Canyon. And so the layering you see in the Grand Canyon is the direct result of water-borne dirt, sediments that dropped down and caused over millions of years the layering in the Grand Canyon. And what's compelling is if you look at Mars over here, there you see some of the same layering. Why, oh why, would Mars have that kind of layering that looks just like the Grand Canyon? One possibility, for sure, is that there were standing bodies of water, lakes and oceans on Mars that deposited in a sedimentary way the silt that caused these layers. Yet more evidence of liquid water on early Mars. And there's no better example, evidence of liquid water on Mars than to just look at the pictures. These look like dry riverbeds here. Here you can see craters where water must have been flowing by the crater and eroded the soil, the dirt on either side, and you can tell which way the water was flowing. It flowed around the rim of the craters and eroded the dirt around it, the crater serving as a block. And here's some more evidence. Surface of Mars that for all the world looks like there must have been flowing liquid water. Of course, we know there's water ice on Mars, so how could there have been lakes or oceans of water on Mars in the past? The only way that could have happened is if the atmospheric pressure got much higher than it is now, maybe only momentarily. How could that have happened? How could it be that Mars in the past had a healthy atmosphere? Well, you could imagine some scenarios. Maybe Mars used to have a thicker atmosphere, but it's lost that atmosphere. Or maybe there were volcanoes that went off on Mars that spewed gas into the atmosphere and enriched Mars's atmosphere, making it a high enough pressure to support liquid water. Or maybe there was an impact. Some asteroid hit Mars and melted lots of rock, spewing up vapors that filled the atmosphere of Mars. You can imagine a number of scenarios in which, for hundreds of years, maybe thousands of years, Mars had an atmosphere with high enough pressure and maybe high enough temperature to support liquid water. So it's pretty exciting to think that the study of water, especially liquid water on Mars, is a precursor to our interest in eventually exploring Mars and maybe even colonizing Mars. There's a remarkable topography of Mars, and I want to point out a few amazing features. This is a map of Mars in which color is being used as a code for altitude. Blue is low altitude, and red is high altitude. It doesn't mean that, obviously, that Mars has these colors, but it gives you a chance to visually see the low-lying areas and the high-lying areas. And if you look at this picture of Mars, this topographical map of Mars, you see some amazing things with your naked eye. You see Valles Marineris, this giant Grand Canyon in Mars. You certainly see some low-lying areas. The blue regions here are very low, as if they were ocean bottoms millions of years ago. Like the oceans on the Earth, the ocean floor, the sea floor, resides lower than the continents. Yeah. That's a good question. I'll repeat it. How do they decide where the 0 point of Mars's elevation is? And here's the answer. It's kind of arbitrary, really, because heights are just relative. You can use the gravitational field of Mars and ask, what is the surface at which the gravitational field is a constant? It's kind of like sea level on the Earth, because the ocean level on the Earth is the level at which the gravitational field is a constant. Otherwise, water would flow downhill. So they use the gravitational field. But where you call 0 is arbitrary. So the blue regions are low. There are obviously big, giant low regions. Look at this, called Hellas Basin. Hellas Basin looks like an impact crater, and it probably is. But it's low because something hit there, dredged out a low region. But the most bizarre and remarkable part of Mars's topography are the volcanoes. You see these volcanoes? Olympus Mons is here. There's 3 more here. There's some smaller ones. Mars has volcanoes. So occasionally the hot rock from the mantle of Mars squirts out like toothpaste through the surface of Mars and causes volcanic eruptions. There's no evidence of plate tectonics. You can look yourself. I don't see any plates at all. I don't see any evidence of plates that are butting up against other plates. So just to summarize, there are features on Mars, differences in elevation, volcanoes, these giant canyons like Valles Marineris, no plate tectonics. Clearly, liquid water existed momentarily, maybe even for longer periods of time on the surface, but there's no liquid water now, just ice instead. Nobody understands why Mars has low regions and high regions. It's a mystery. And I've asked some of the experts, they still don't know. One of the most famous regions on Mars is this volcanic region. It's called Tarsus, the Tarsus region. Here you see the giant 4 volcanoes. And it's probably a good idea if you want to memorize something about Mars and impress people at cocktail parties. You can talk to them about the enormous volcano Olympus Mons, which is larger than Mount Everest. So the tallest mountain of any sort in the solar system is this Olympus Mons that exists on a relatively small planet. And here you see it magnified. There's Mars, there's Olympus Mons, there's Olympus Mons, a real picture of it, and here's another picture. Largest volcano in the solar system, not just Earth, but anywhere. How big is Olympus Mons? Well, here's how big it is. There's Olympus Mons, and there's Mount Everest, a little puny thing. So Mount Everest would just be a little blip compared to this enormous volcano. And I think I'll just stop with 1 or 2 last slides. The atmosphere of Mars, I've mentioned several times, is thin, but it's not so thin that you don't get beautiful sunsets. When the sun sets on Mars, the dust particles in the atmosphere scatter the sunlight a little bit like they do on a smoggy day in Los Angeles. And when the sun sets, it becomes kind of red. The air becomes kind of reddish. And so you might imagine someday, or maybe it's your children or your grandchildren, will be sitting with their sweetie in the colony on Mars, watching the beautiful sunset over the hills on Mars if they are living there. So I'll stop there, and next week we're going to talk about atmospheres and global warming.